Hello, everybody. I am Rashid Sheikh from Lund University, and welcome to this lecture, which will be about multi-objective optimization. In the previous lecture, we have studied single objective optimization, in which we have only one objective function to either maximize or minimize. And today we will cover more advanced topic, in which we have like many conflicting objective functions, and we try to either maximize them or maximize some of them and minimize some others. So let's start. So our journey will begin with an introduction to the fundamental principles of multi-objective optimization, followed by an exploration of classical methods that involve the conversion of multi-objective problems into single objective ones. We will then uncover the concept of Pareto fronts, which is a cornerstone of multi-objective optimization and tries to make trade-offs between competing objectives. Moreover, we'll delve into evolutionary multi-objective optimization with the focus on a specific technique, which is NSGA-II, non-dominated sorting genetic algorithm 2, which harnesses the power of evolutionary computation to navigate the complex landscape of multi-objective optimization problems. So let's do it step by step. So let's first start with defining the multi-objective optimization. Actually, multi-objective optimization is an area of computation and operations research that focuses on multi-criteria decision making and that deals with optimization problems involving several objectives to be optimized simultaneously. Those objectives are formulated as functions and they are often conflicting and competing. Let's consider, for example, the case of price vs quality. Imagine you are trying to find the best solution for a problem, but there are different goals, like wanting something cheap, but also with good quality. So multi-objective optimization will help you with such situations. It deals with problems where you have several things to improve, like price and quality, but they might not agree with each other. Multi-objective optimization tries to figure out the best balance or compromise. It's like finding the sweet spot where everything works out as well as possible, even though different goals might be pulling in different directions. Minimizing a vector comes back to define the optimality. Problems usually conflict in nature, and thus the designer should make a trade-off, a compromise. Into this definition, the main aim of multi-objective optimization is to give us a bunch of solutions that show the best compromise between different goals, different objectives. So these optimal solutions, known as Pareto-optimal solutions, are like the top choices where none of them is better than the others when you look at all the goals together. But to get there, we need to follow a few important steps. So first, we have to describe the problem in a way that really reflects the reality, shows what's happening in real life. Then, we need to decide on the things we want to make as good as possible, which we call objective functions. So we need to formulate objective functions. This is the second step. Then, in the third and final step, we either create new methods or use ones that already exist in multi-objective optimization landscape to help us find best optimal solutions. So it's like a step-by-step process to make sure we find the best trade-off between different goals in a problem. So multi-objective optimization is a helpful tool used in different areas to make decisions. Let's look at an example where multi-objective optimization is used for sustainable logistics, which means making sure things are good for the environment, human, and economy. When we talk about multi-objective optimization in this context, we have different goals to think about. First, there are economic goals like how much it costs and how well it works and how long it takes and so on, and how reliable it is. Then there are sustainability goals like how much it affects the environment and how much its use of energy and water and produces waste or noise. Lastly, there are social goals like how it is benefit for people, for human beings, how many jobs it creates, how it keeps employees safe and helps communities and so on. So multi-objective optimizations helps us to find the best solution that balance all different goals when we are dealing with things like logistics, making sure we make good choices for the economy, the environment, and people.
After explaining what is multi-objective optimization and its role, let us see how it can be reformulated mathematically. So the output that multi-objective optimization tries to figure out is the best values for a set of decision variables. So these decision variables helps us to make decisions and do different things. The idea here is to either make something as small as possible, this is what we call minimization, or as big as possible, and this is what we call maximization. So some of the objectives have to be minimized and some others should be maximized. So this is depending on what we are looking at. These things we want to make small or big are called objective functions, as we have described before, and they can be more than one of them. For example, here in our case, we have n objective functions. So we have some rules or conditions to follow, though, and they are called constraints. Therefore, we want to make sure our decision variables meet certain requirements, which are described by constraints. So constraints are like some specific rules that should be respected by the objective functions or by the solutions. These constraints can be either less or equal to for some variables or equal to for others, which means that we have inequalities and we have qualities. So multi-objective optimization helps us to find best values for our decision variables that make our objectives as good as possible while still following the rules or constraints we set. So this is like the general definition of the workflow, and it's smoothly formulated in mathematics equations. To summarize, multi-objective optimization can be formulated mathematically as a framework to optimize the vector value objective function if x and satisfies a set of constraints. But here comes an important point. Even if we find solutions that meet all these rules, we can't call them perfect for all the solutions. They might be great for some, but not for others. So it's a bit like a balancing act, finding the best compromise that fits within the given rules, but not perfect for every single function. Before delving into the methods and the practical side of this lecture, let's explain the most important notions, and let's start with the concept of decision variables. So decision variables are the dynamic elements in the optimization problems, essentially the levers that decision makers have at their disposal. Think of them as the adjustable components that we can tweak and fine-tune to steer towards the best possible outcome. So they are variables that actually we are controlling in order to change the output and then evaluate iteratively the output in order to achieve the best solution. Now, why are these variables so crucial? Well, they serve as representation of quantities or parameters that we need to figure out in order to optimize what we call the objective function. The objective function is essentially our goal or criteria that we are striving to either maximize or minimize. So In essence, decision variables are the tools in our optimization toolkit, allowing us to navigate and manipulate the factors that lead us to the most favorable results in our decision-making processes. Alright, let's dive into the heart of solving a multi-objective optimization problem. Picture this as a quest to discover the best solution. So what does that involve? Firstly, we have what we call the search space or decision space, denoted as X, big X, which is essentially the universe of all possibilities where our solution could exist. It's like the playground for our decision variables. Now we add a bit of reality check. We introduce the feasible search space, represented by X bar, which is a subset of X. This subset is where we find solutions that meet the criteria we have already defined as constants, which means that this feasible search space, is a set of solutions that meet the constants Cx lower than 0 or Hx equal to 0. These are the valid, doable solutions we are interested in. But of course, not everything in X is going to fit the bill. We have what's called the infeasible subspace, denoted by X minus X bar, which contains solutions that are impossible, that are infeasible. So, in a nutshell, solving a multi-objective problem is like embarking on a journey within this decision space, exploring possibilities and different combinations, but only considering the ones that align with our predefined criteria, predefined constraints, and also that optimize our objective functions. It's the art of navigating through the feasible search space to uncover the optimum vector that satisfies our multi-objectives in the objective space.